Welcome back to Micrium's offices for the second video in our three-part series on multitasking. I'm Matt Gordon, and in this video I'm going to be discussing 5 important API functions for Micrium's real-time kernel, MicroCOS3. A kernel's API, or Application Programming Interface, is the collection of functions through which application developers deploy the kernel's services. Although MicroCOS3 can seem somewhat complex to the uninitiated, there are actually just a few API functions that you need to know in order to begin writing multitask applications with this kernel. OS Init is necessarily the first MicroCOS3 API function invoked by any application that incorporates the kernel. Like all other MicroCOS3 API functions, this one can easily be recognized as part of the kernel because of its OS prefix. The init that follows OS indicates that the function performs kernel initializations. For the most part, these initializations consist of operations that are common to pretty much every C program, such as setting pointers and arrays. However, one of the responsibilities of OS Init is to create MicroCOS3's internal tasks, an initialization that is clearly specific to multitask applications. MicroCOS3's internal tasks perform a variety of jobs, including keeping statistics, offloading work from interrupt handlers, and updating the data structures involved in different kernel services. How many of these tasks exist alongside an application's own tasks depends on how the kernel is configured. One internal task that is always present, though, is the idle task. This task is run by the kernel when there is nothing else to do. In other words, it is run when there are no application tasks ready to run. Although OS Init is responsible for performing numerous initializations, its prototype is somewhat simple. The function accepts just one argument, a pointer that the kernel can use to return error codes. This means of conveying errors is standard across the MicroCOS3 API. The kernel indicates whether a particular function completed successfully by dereferencing the function's error pointer and placing an integer value in the resulting memory location. In a MicroCOS3 application, the OS Init call is made from main, where it is typically followed by a call to another of the kernel's API functions, OS Task Create. This is the function through which we, the application developers, create our own tasks. The prototype of OS Task Create, with its 13 arguments, can be a little intimidating to developers who are not familiar with MicroCOS3. However, all of the arguments are thoroughly described in the kernel's documentation. We'll go over just a few of them here. The first argument passed to OS Task Create is a pointer to a TCB, or Task Control Block. A TCB is one of 2 data structures that a MicroCOS3 application must declare for each of its tasks. The second, a stack, is also passed to the kernel through OS Task Create, in this case through the 6th argument. It is important to remember that application code never manipulates stacks or TCBs. These data structures are managed by the kernel. In order to actually run a task, the kernel must have a reference to that task. Here, reference simply means a function pointer, since MicroCOS3 tasks are C functions. A task's function pointer is passed to the kernel through the 3rd argument of OS Task Create. The 5th argument of OS Task Create, and the last that we'll review in this video, sets the task's priority. As I mentioned in the previous video, priority helps the kernel to decide when a given task should be executed. In MicroCOS3, priority is an integer value, with lower values corresponding to important tasks and higher values corresponding to relatively unimportant ones. A task with priority 2, for instance, would take precedence over a task with priority 7. Of course, the task priority established through an application's initial call to OS Task Create won't become important until the kernel begins running tasks. The API function that prompts the kernel to take this step is called, appropriately enough, OS Start. This function accepts a single argument, a pointer, that is used for returning error codes, just like the pointer passed to OS Init. OS Start is usually the last function called from main. It is preceded, in most cases, by just one OS Task Create call. There are a few reasons why multiple OS Task Create calls should not be made from main, but we won't get into these details now. It is important to remember, though, that a single OS Task Create call in main certainly does not limit an application to just one task. Other tasks can be created after OS Start has been called. Microc OS 3 allows tasks to be created pretty much anywhere outside of an ISR. In a typical Microc OS 3 application containing a single OS task create call in main, the task specified in that call is the one that is executed by OS Start. After the handoff to the task, Microc OS 3 is officially multitasking. OS Start does not return, and any functions following it in main are not executed. Although the three API functions that we have discussed so far, OS Init, OS Task Create, and OS Start, help us get the kernel up and running, we need to employ at least a couple more functions in order to actually write a multitask application that does something useful. Microc OS 3 offers a number of services that enable developers to write robust multitask applications. But in this video, we're going to limit our discussion to the kernel's inter-task communication services. In particular, we'll look at Microc OS 3's task queues. In a kernel-based application, queue typically refers to a data structure that tasks can use to pass messages to each other. Queues are managed by the kernel, and tasks access them through API functions. Two different varieties of queue are available to developers of Microc OS 3 applications. In addition to offering the task queues that I just mentioned, the kernel also provides what we can call standard queues. These two types of queue differ in terms of overhead and functionality, with the task queues involving slightly less overhead than their counterparts, but offering somewhat fewer features. We're going to examine two API functions associated with Microc OS 3's task queues, the first of which will be OS Task Queue Pinned. This function allows a task to retrieve a message from a queue. If a task calls OS Task Queue Pinned and no message is available, the kernel will pass control of the CPU to a different task, allowing the application to continue doing work even while part of it waits for data. OS Task Queue Pin accepts 5 different arguments, but for now we'll focus on the first one, Timeout. This argument allows a task calling OS Task Queue Pin to specify the maximum amount of time that it is willing to wait for a message from the queue. If a message is received before the specified timeout period elapses, then the task can access the message through the return value of OS Task Queue Pin. If, on the other hand, no message is received, the task will receive notification of the timeout through the function's error pointer argument. Messages are placed in a queue much as they are removed from one, via an API function. The function for adding messages to a task queue, OS Task Queue Post, somewhat resembles the pin function. However, adding or posting messages to a queue is not a blocking operation, meaning that a task never has to wait to post. Accordingly, the post function has no timeout argument. This function's first argument is instead a pointer to a TCB, the data structure that I touched on earlier. In Microc OS 3, when task queues are enabled, each TCB contains one of these queues. Thus, the first argument to OS Task Queue Post is what tasks use to identify a particular queue as the target of a post. The actual message being posted through a call to OS Task Queue Post is passed to the function by way of its second argument. This message can be of practically any type, since the third arguments of both the pinned and post functions allow tasks to share the size of a message. A posting task specifies its message's size through the third argument of OS Task Queue Post, while a pending task determines the size of a retrieved message using the memory location referenced by the third argument of OS Task Queue Pinned. The 5 functions that we've just covered make up only a small portion of Microc OS 3's API. However, you'll need little more than these functions to begin writing your own multitask applications around the kernel. In the final video in this series, I'll present a few such applications and discuss their contents. If you're ready to embark on your first kernel-based project, then you shouldn't miss this guided tour through actual Microc OS 3 application code. Goodbye, and thanks for watching.